Okay.
So welcome everyone to HAO Colloquium. Our today's speaker is Robert Cameron. Robert Cameron is a staff scientist at the Max Planck Institute for Solar System Research. He is interested in the interplay between flows, magnetic fields, and radiation in the solar interior and its atmosphere. Today, Robert will be speaking on a delta omega Babcock Leighton solar dynamo.
Okay, thank you very much. So most of this talk will be about or the new plan is flux emergence and the gel effect. But to put it in the context, I'm going to begin with why this is important. So we're trying to understand the dynamo, and the big advantage we have over, say, 40 years ago is computer power and observations. So now I'm going to mainly concentrate on the observations. So we have observations of the magnetic field at the surface, including the toroidal field. So here mainly the radial field of the surface, and the toroidal field, which is the azimuthally averaged phi component of the field. And we've got this for 4 cycles now. The framework I use is, of course, the induction equation. I will use Stokes theorem a few times in this talk. Stokes theorem converts the induction equation into a line integral. If you integrate the induction equation over some area, it turns it into a line integral. I'm going to assume the molecular diffusivity is small, and use the usual symbols for axisymmetric mean and perturbations to that mean. So the toroidal flux budget is what we get if we apply Stokes theorem to the area enclosed by this contour. And it tells you the change in the toroidal flux threading, for example, the northern hemisphere, is given by a line integral over this contour. And the line integral is made up of a part which is the mean field and the mean flow, and a part which is the mean of the cross product of the perturbations. The first term, the mean U plus mean B, gives you the amount of field which is generated by the large scale flows of fields, in particular differential rotation acting on the magnetic field threading through the photosphere. And if you calculate this, it turns out to be about 5 to 8 times 10 to 23 Maxwells per hemisphere. So this is how much is generated by magnetic field threading through the photosphere in the northern hemisphere. You can also calculate the loss through flux emergence, and this turns out to be a similar number, about 3.3 times 10 to 23 Maxwells. And these two are roughly equal, and this is the toroidal flux budget. So in more detail, we consider each of the segments, the interior axis, photosphere, and equator shown on the right, one by one. We place our contour inside the interior, beneath the in the radiative interior. So the axisymmetric component, which varies on a 22-year cyclic component, should be very small. And we move into a coordinate system rotating at the equatorial rotation rate, and we notice that the rate at the equator the rotation rate is more or less uniform. It's above 460 for most of the radii, and only very slightly near the surface and near the tachocline. So the contribution from this component is also small. The contribution from the axis is small because there the large scale flow and field have to be, well, they've got no phi or theta components. So this leaves us with the contribution coming from the photosphere. And the nice thing about this is all the quantities there we can measure and have been measured. And it's important they have been measured because I won't be measuring them. And this is what they look like. We've got the surface radial field, the axisymmetric component, and we've got the axisymmetric flow field, which is the differential rotation of the surface. We multiply these two together and we get the integrand. And we integrate this, for example, from 0 to 1 to get the amount of toroidal field generation rate for the northern hemisphere. You do this and you get the quote figure I showed before, 5 to 8 times 10 to 23 Maxwells per cycle per hemisphere. You can now calculate the loss term. So it's the same equation, but now we consider the fluctuating, so the axisymmetric mean of the fluctuating U times the fluctuating B, the cross product. And this corresponds to flux emergence. So here I need to explain the observations we saw before of the phi component of the field come from flux emergence. When flux is emerging through the surface, during the emergence process, the loop top pokes out, is seen at the photospheric level, imprints itself on the Stokes V at the limb, for example, and can be observed. And the blue and the red shadings are the inferred phi component of the field, axisymmetric average, from the WSO data. So it goes back 40 years. The dots are sunspot locations, the black dots, and you can see they nicely overlie the regions where we have strong toroidal field emerging from the surface. This is because the toroidal field which is emerging produces those sunspots. And you can see at higher latitudes, we have emergence of ephemeral regions, which are also seen in the axisymmetric toroidal field. And this is because as an ephemeral region emerges, it carries toroidal flux across the surface where it can be observed. So this is a B phi due to emergence. The velocity of the emergence, the radial velocity, is about 1 kilometer per second. And this allows us to calculate the amount of toroidal flux, which is lost at emergence, which is about 3.8 times 10 to 23 Maxwells per hemisphere per cycle. You can also, people have also, Bieber and Rast, estimated it from measurements of the field from in situ observations of the solar wind, and you get about 5 times 10 to 23 Maxwells. So this is nicely consistent. And the point I want to make is basically what we generate by winding up field which threads through the surface of the sun is what we lose through flux emergence. We also have, I will show next, so when we generate more toroidal flux, we have more flux emerge. And this is why we have this strong relationship between the minimum AA index of a cycle and the amplitude of the next cycle. So the minimum AA index is taken near the time of minimum and is a measure of the open flux of the sun, which at times of minima is a measurement of the strength of the polar fields. And this is because the integrand because the integrand for the explanation for this figure, which also relates to Wang and Shealy, comes from this. So when we have the polar fields are the integrand for the amount of toroidal field we produce. So if the polar fields are stronger, then we produce more toroidal field, and therefore the next cycle will be stronger. And so the x-axis is a measure of the toroidal field generation, and the y-axis is the toroidal flux loss due to emergence. And you can add cycles 24 to this, and within the noise level, you can also add cycle 25. It's currently observed. So here we see cycle 24, and cycle 25 is got a higher minimum AA index and turns out to be about 150. So it will fit nicely on this plot. The next question, and the part which this talk is more focused on, is where do these polar fields come from? So now, if we have the polar fields, we will generate the toroidal field, and we will have flux emergence. We want to now understand where the polar fields come from, and we're going to simplify this question by asking how does the polar field change between one minima to the next? So we avoid having to consider the details of the butterfly diagram, basically. And because you can see from this image, the field at the end of the cycle is concentrated at the poles. So at T1 and T2, all the field is concentrated at the poles. Because this is in terms of cos theta, it's equal area per on the y-axis. So the y-axis is equal area, therefore, so it's all white in the middle and blue red at the poles, tells you that the total flux in each hemisphere is dominated by the polar fields. So we can ask ourselves, instead of how do the polar fields change, we can ask how does the net radial flux in each hemisphere change? And this is a nicer question because we can apply Stokes theorem. So we apply Stokes theorem. In this case, the area is the entire northern hemisphere, and the contour is the equator at the photospheric height. You apply Stokes theorem, and it tells you all you need to look at is flux crossing the contour at the equator at the photosphere. And this is nicely observable. And there's two ways flux can cross that surface. We can have a URB feeder or a U feeder BR. And they're both observable, as indeed is the total flux in each hemisphere. So what happens when you do this? So here we look at the different ways the two terms contribute. So first of all, you have got a contribution from URB feeder, and this is when flux emerges across the equator. So if you have north-south aligned tube, which emerges through the photosphere at the equator, it will carry flux across the equator, and in this case, the positive flux ends up in the northern hemisphere, and the negative flux ends up in the southern hemisphere. This is a random process. The tilt angles of these active regions has a large amount of scatter and is, we believe, due to convective buffeting and is apparently random. The other contribution is more interesting. So it has a random component coming from the convective buffeting, as described, but it also has a systematic component. And this systematic component leads to opposite polarities, well, basically corresponds to Joy's law and Hale's law. So Hale's law tells you that there's an east-west orientation in each hemisphere in each cycle, and Joy's law says that there's a corresponding preference for a north-south orientation of the two polarities. And this switches from cycle to cycle and is opposite in each hemisphere, and it's why you get this systematic pattern. The systematic pattern, the systematic pattern comes from the emergence of tilted active regions and the subsequent evolution by the surface flows. And this plot is an explanation for why the polar fields end of cycle 23, so the prediction for cycle 24, was not accurate. And the reason is that by this random buffeting of the active regions, the tilt angles during this cycle or at least their contribution to the change in polarities, net flux between each hemisphere, was overestimated if you use a simple Joyce law. If we use the actual tilt, then Joyce law with the observed tilts nicely reproduces the observed change in flux in each hemisphere. So the question then is, and the question which is the new part, is where does Joyce law come from? So Joyce law is a weak tendency. So you can see here at the bottom we have before emergence. We have emergence at t is equal to 0 and emergence 2 days to at the end of the emergence. And there's a slight east-west, there's a strong east-west separation between the polarities and a slight north-south separation. This is Joyce law, and it's what produced this large-scale pattern seen in blue and red on the right figure of this panel, this page. So it's obviously the Coriolis force. It could be acting on convective flows. It could be acting on flows associated with the buoyant rise of flux tubes. It could be acting on some other flows. I'm going to address this question by looking at the observations. These are the people who I've been working with. And you'll see some people here who do simulations. So we'll also discuss the simulations. This is an example of flux emergence seen by HMI. I'm not going to say typical because they're all quite different. But the point, one important point is they're all compact. You can draw a circle around them and the flux emergence occurs in a localized region. The ones we're analyzing here are particularly not representative because we've chosen ones which are away from other active regions. We want to analyze the emergence, not the pre-existing flux, which may be around them. So Hannah made a data set of 160, I think, active regions which were clean in the sense that there's no other active region which emerged a few days before or a day or two after. These are clean events we can observe nicely. And of course, I'm interested in what produces the separation in longitude between the positive and negative polarities, and what produces the separation in latitude between the two polarities. And with a little bit of, with some vector identities and Stokes theorem, I can write the east-west separation in terms of a radial velocity carrying east-west field through the surface and a contribution of the surface east-west flows carrying radial field at the surface. So there's two contributions, one corresponding to flux emerging from below, which the two polarities will then be separated. And the second component, which is due to stuff which is emerged or has emerged, appears at the surface, and then is acted on by the flows associated with the emergence.
I could starting point before you allow them to be moved around.
Yeah, so they have to. So at the very beginning, there's nothing. There's just a blank slate. Then what happens is we have east-west in aligned field, which emerges through the surface.
Okay, but it starts off being aligned in latitude.
This will need to find out.
Oh, okay.
But it will have the latitudinal separation will come from the east-west component of the field being carried across the surface. Then you have a positive at one end and a negative at the other end. So your radial field will be a bipolar pair, and they'll be separated by the amount of flux you brought across the surface.
Yeah.
And there'll be a corresponding, it's showing north-south separation, which has a similar mathematics. And you need Stokes theorem essentially to, because you have a contribution from flux coming in from the red circle. So if flux crosses the red circle, then of course you have to include it. But because we've chosen isolated regions and because we've chosen contours which enclose the active region entirely, the expectation value for that is 0. So we can ignore it. These bars here mean expectation values. which is why we're getting null. Yeah.
The quality you're calculating, like the length.
Yes, so it's a separation of the two polarities multiplied by the amount of flux. Yeah, and so to get so this is a separation multiplied by flux, and to get the Joyce, of course, I can just divide these two, and the flux will be the same.
Like flux weighted.
No. It's not flux weighted, because it's multiplied by the flux. So the units for this will be Maxwell.
Maxwell.
Maxwell length.
So yeah, so
It's not flux weighted because that would be
okay.
yeah.
If you divide by the flux.
Yes. If I divide by the flux, okay. So now I can measure the north-south separation at each instant in time, and I can measure from local correlation tracking or helioseismology the U phi. I can measure the BR. I have difficulty measuring the UR, and particularly the B phi, because of 180-degree ambiguity, because of noise. I can measure the term on the left, and I can measure the last terms on the right. And this is what they look like. So the east-west separation flux multiplied is shown in blue on the left panel. And the contribution coming from surface motions in the phi direction, so U phi BR integrated over time, integrated over the area, the time being the time from emergence, is shown in the yellow curve. This is an average over all the flux emergences and observed in her catalog, which is more than 100. And what you see is all of these terms are important. I can now look at the same, but in the north-south separation. And here we see something different. The blue and the yellow curves are almost the same. And this is telling me that the north-south separation is not coming from beneath the surface. Compared to the east-west separation, there's no substantial north-south separation coming from beneath the surface. The separation we see in the north-south direction is coming from a U feeder motion carrying radial flux at the solar surface. And this, I think you should find surprising. I found it surprising, which is why I wrote a paper. So the picture for what's going on is similar to what would be an alpha effect. It's actually going to be called a Mandela effect, but we have motions, radial motion carrying flux through the photosphere. We have horizontal motions carrying the flux apart. The horizontal motions are acted on by Coriolis force, producing a U theta and producing a north-south separation of the two polarities when they move according to the flows. So here is, for comparison, an ASH simulation. So this is an ASH simulation of dynamo action in a configuration which is not too far from the sun, although the magnetic fields of course look very different from the solar ones. And of course, so this is the surface magnetic field, or the magnetic field at the upper boundary of the simulation, and the simulation has an impenetrable boundary condition, so I'm going to call it the surface of the simulation. You can see it's got magnetic field poking through the surface, and the only way for that to stay there is if we have flux emergence. And because the surface is impenetrable, the flux emergence necessarily involves a diffusive flux. So I look for places where there's a strong radial diffusion of horizontal field.
Sorry, is the magnetic upper boundary condition falls to normal?
No, this particular one is potential. I think the result would be similar,
If it
but
falls to normal.
yeah, but this one's potential. So I'm looking now for flux emergence. So I'm looking for locations where there's a strong radial gradient of the horizontal field, so B5 and B theta. And what I do is I choose the 6,000 locations where, no, 12,000 locations where this is where the radial gradient of the horizontal field is strongest. And then I average them in such a way as to account for the cyclic variability of this dynamo. And this is what the BR looks like when I do this. So the crosshairs shows the location where I've looked for the emergence. So I've looked at a particular latitude and I've created the average emergence by taking all the emergences at latitude and shifting them so that they all at the zero longitude. So the appearance in here of in the middle plot. So the middle plot shows me the diffusion of the phi component of the field for the surface, and you can see that close to emergence, so one day after emergence, it's strongly concentrated at the emergence location. And this was more or less my definition of what an emergence should be. My definition again was the actual two components of the field, B phi and B theta, but the B phi one dominates. Before emergence, the actual emergence event, you have a little bit enhanced emergence at location, and a little bit after, you also have enhanced emergences. You can see also, so we have strong pre-existing radial field at the location of the emergence. This, on the sun, we would call this nesting, but whether or not this corresponds to nesting is beyond the scope of this talk. If I look at the third panel, it tells me the perturbation to the difference with respect to the mean flow of the phi component of the motion. And if you look here, you can see that the pattern we observe is much more extended than the location of the emergence. It basically goes from the northern hemisphere to the southern hemisphere, and the shape is the shape of a banana cell. So this is the average flux emergence in the ASH simulation, dynamo simulation, corresponded to the location of a banana cell, a particular phase of a banana cell evolution. And the U theta, the perturbation to it, we also see structure, which at this latitude corresponds again to the banana cell. The banana cell is only present outside the tangent cylinder. The convection has a different functional form inside the tangent cylinder. Yeah, and this is just standard convective patterns for these type of simulations. The important point is on the next page.
Before you go to this page, though, and it's not an important point, I suspect, but it's a confusing one for me. The left-hand plot shows that you've got a good polar field. The red on the top, the blue on the bottom. What's the blue at 50 degrees?
Yeah, so this isn't the sun. This isn't ASH simulation. So this has more structure in the differential rotation. There's actually got shear there at some mid-latitude.
Okay.
And so a lot of this structure is not directly comparable to the sun, but some of the processes are. This is why we're looking at the flux emergence process in the simulation. Of course, I'm not saying this is not like the sun because I don't want to get into trouble. But now we can do the same as we did. Now, since we've got the average simulation, average emergence, we can also calculate the longitudinal separation and the different components as we did for the observations. So the blue curve shows the total as a function now of latitude. So before I showed at different times the average over all latitudes, Now I'm just going to show you the after 1 day, but at different latitudes. And what you see is for the longitudinal separation, the contribution from U5BR is small. So this is telling you it's mainly coming from turbulent diffusion carrying, in this case, diffusion, carrying the phi component of the field across the surface. So this is not quite the same as the sun, but somewhat similar given the constraints of the simulation. The latitudinal separation is quite different. So on the sun, we only have observations up to about 40 degrees. And what we saw there was the blue and the yellow curves overlapped. And this was the statements that the flux which is emerging from below basically has no chill. Here you can see at low latitudes, it's not quite true. There's more structure, but suddenly at high latitudes, there's a substantial component coming from not coming from the U5BR. And this is coming from processes beneath the surface which have tilted the tube before emergence. So this would be an alpha process, for example, acting in the bulk of the convection zone. The yellow curve, however, still resembles the observations, and this is the component of the north-south separation coming from surface flows acting on the radial field. And now I want to place this in the mean field framework. So I have to introduce the EMF. And the EMF comes straight from the induction equation where you label the U prime cross B prime, so the fluctuating cross product azimuth for average thereof as the EMF. The EMF in the mean field framework, we expand to lowest orders as A dot B plus B dot nabla B. So this is in covariant form. If you write it out in detail, it has all these terms. So B here is a third order tensor and A is a second order tensor. Fortunately, some of these terms are going to disappear. For a start, in the simulation, the mean value of B phi is equal to 0 at the surface. This is a consequence of having a potential field. It would be the same if we had a radial field, and this is almost true on the sun, except during flux emergence processes. So we can cross out all the terms which just involve B phi. If we look at the structure of Joyce law, well, Joyce law turns out not to depend, it's the same everywhere across the butterfly diagram. So there's a latitudinal dependence, but it does not depend on the sign of the field. So you can see in the top picture, for example, in the first cycle, you look in the southern hemisphere, some of it's blue, some of it's red. Joyce law doesn't care if it's blue or red. Joyce law does not depend on the radial field. So we can now cross off all the terms involving the radial field. You can also cross off the terms which involve the mean B theta and the mean and the radial derivative of BR with respect to R, because these are determined essentially by the radial field at the surface. So in the potential field model, they're exactly determined by BR at the surface, the spatial distribution of it, and in observations, again, the component associated with flux emergence, these should vanish. This leaves you with two terms. One is B phi theta R, and the other is B theta R, and these act on radial derivatives of the horizontal field. But we saw from the observations that the contribution coming from the radial derivative of B theta was small. So we're not carrying north-south component of the field through the surface. So now this equation I'm now more happy with because there's only one term left. This is the phi component of the EMF due to flux emergence corresponds to beta phi phi r times the radial derivative of b phi. And it's this EMF due to emergence which is producing Joyce law. And so this creates a north-south separation of the two polarities at the surface. So this is what's generating the polaritic field that we observe at the surface, and which then feeds back into the whole dynamo process, produces the polar fields, gets wound up, produces toroidal field, emerges, closing the dynamo loop. I could have left it at B phi phi r, but usually we express it we can write the EMF in terms of alpha, gamma, beta, delta, and kappa. In which case the B phi phi r goes into the delta and the kappa. And so the dynamo action due to the delta was studied by Rader in the 60s and is called the Rader effect. Kappa is usually less spoken about because you can give a nice, simple physical interpretation to the alpha, to the gamma, to the beta. So the beta is a diffusivity, the gamma is a pumping velocity, the alpha is the generation of polaritic field due to forcing convective motions. The delta here corresponds to the off-diagonal terms of the diffusion tensor, but the kappa is it's just a catch-all for all the bits which are left and more difficult to give a physical meaning to, and therefore I end up with the observations indicate that the solar dynamo is Babcock Leighton delta omega flux transport problem. This is the end of my talk. So questions, and I imagine there'll be a few.
I have one, or maybe two. So maybe I didn't understand you properly. When you talk about the latitudinal separation and being dominated from surface motions, are you saying that they act before the emergence happens, or does it emerge and then the
So it has to emerge and then happen, but it happens within 1 or 2 days when you still have correlations between the emergence magnetic field and the velocity pattern. So emergence, the field emerges the field emergence itself creates no north-south component of the field, separation of the polarities. Instead, the flux emerges on average east-west aligned, and then it gets acted on in the north-south direction.
Okay, so from an observational point of view, when you use the HMI observations, and
so we use the HMI.
Yeah, and the fact that you chose isolated emergencies, do you think that is there any reason to think that those ones might be biased because there is less interaction with other stuff around once it?
So you have lots of, so it's very complicated to analyze. The reason we chose these ones.
I understand why you chose them, right? It makes it much easier, but I just wonder if the emergent forces
associated with an active region, and these can have an effect, and the effects have been investigated to some extent based on pure models. in a series of papers we wrote with Manfred in the from 2010 onwards. So we have large-scale inflows to the active regions, and so depending on where you emerge relative to the active region, you can have you see this flow, and the flow will see one polarity more than the other, and this can produce changes. I don't think that has a strong systematic effect. I think you can see. So this, okay. So first of all, we still have something similar in the north-south separation from the surface flows when we look at the simulations. We also have other stuff coming off, but here it's clear it's the north-south, and here it's also clear that this is coming from the convective flows. So here the magnetic field is not strong enough to drive large-scale flows, and here it's coming from the convective. This is why we can see the nice banana cell convective pattern. On the sun, I can't give a definitive answer, but my guess is it's not hugely different.
Please go ahead.
Okay, you can't measure UR. How can you measure UR when you do?
And so I don't measure UR. So I don't measure UR.
Oh, he just assumed.
So I measure. So there's three terms here. So I can measure the one in blue. I can measure the one in yellow. And the difference is, and this is why here.
It's already matched. Okay, so there's no more contribution from the black.
Yeah. So this is the point here. The blue on the right-hand panel. The blue and the yellow basically match, which means I've got no contribution coming from the black. Yes.
Travis.
And this is surprising because it's telling you that before emergence, the field just beneath the surface is east-west aligned. And why should it be east-west aligned just beneath the surface? So all the thin flux tube models would tell you that this should be dominated by the black zone. And alpha effect operating deep in the convection zone would also be dominated by the black zone. That happens at the surface where your B5 vanishes in the simulations and is smaller due to flux emergence in the observations. It's telling you, and Joyce itself, it's telling you that it's the actual emergence of the field through the surface. And the correlations between where it emerges and the surface flows, which is giving you Joyce.
Why is it not more random as to which way it's oriented if it's happening right at the surface and then it's tilted because of the local flows?
Yes, but because
Travis has a question also written there. After that.
I'll answer this one first. Okay, so you can see here, compared to so in the case of the simulation, it's easy. The flux emergence occurs at a particular location relative to the convective field. And so it sees, on average, a particular type of flow structure associated with the convection. And so flow structure is what's causing the separation. So it emerges, if it emerges at random places with respect to the flow field, then it would be, of course, average out. But it doesn't. It emerges with a tendency to emerge in a specific location relative to the convective pattern.
Okay.
And a similar thing has been seen on the sun, where the emergences, you tend to emerge at locations which the day before were inflow regions, east-west aligned inflow regions. And this is a result of Aaron Birch. So we're emerging in a specific location of and not just randomly compared to the convective pattern.
Yeah.
Okay.
Travis, you can unmute and ask.
He's not muted. He's not connected.
Is that question? Yeah, yes, his question.
it's
Oh,
the
no
mic.
mic. Okay.
Yeah.
This question is the relative influence of differential rotation and meridional circulation relevant to this picture? For example, DR is strong and MC is relatively weak.
Yeah. So the differential rotation occurred in the first half, where you determine how much toroidal field is generated from colloidal field. I did not discuss the meridional circulation in this talk, but meridional circulation is one possibility for moving, well, it certainly moves the flux at the surface from the pole towards from the equator towards the pole. And what causes the return of the butterfly wings latitudinal propagation towards the equator is more ambiguous. It could well be meridional circulation transport. It could also be flux pumping. It could also be some other type of dynamo process. This is not well constrained by the observations I've considered here. So I don't know the answer to your questions. More that's what I said.
Okay. Question. Wow.
The interpretation I can see is that you're saying activations are not coming from deep inside.
No.
In order to finish not have these data when you approach the surface. Otherwise, if they're coming from the deep part and then they will expand as they got had before emergence. You're basically saying they are coming from the surface. They generate
No.
activations.
I'm not.
Isn't
I don't understand. Well, I don't understand the dynamics occurring beneath the surface because I don't understand how convection works, for example.
Okay, at least the convection works based on what Ash is saying.
Yeah.
The
Okay. Yes.
nanocells that if
Yeah,
it-
but in ash, you have stuff coming from
Right,
which is
you're
not.
saying that's not true.
Yes, I'm saying this is not true. Yes. But we know this is not true. We don't see banana cells. The ash simulation is dominated at low latitudes by banana cells. It has giant cells. We don't see giant cells on the surface, on the sun. Well, we don't see evidence for them at depth. We don't know how convection works or I don't know how convection works on the sun. And this is a convective conundrum, and I think it's super interesting problem.
If the rising flux, whatever flux, if it's coming from the deep interior and if it's coming out because this large scale convection, if it is playing any role, then the Coriolis force should produce that already.
Yeah, so I'm saying the tilt is not there, and if you want to make that interpretation, you're more than welcome. I would not disagree.
Yeah, so another way might be what's magic about the surface. You could go deeper, but you're constraining it to your observations say that at the surface everything emerges purely east-west.
Yes, so at the surface, the north-south separation, which produces Joyce law and which produces the regeneration of the polar fields, is coming from surface motions. Why? So, yeah, Matthias will ask, always does. Why isn't it one of the many other mechanisms which people have suggested? Okay, so if you're talking about thin latitudes, then it's not so simple. They don't all give you Joyce law. Some of them will give you anti-Joy. You can get whatever result you want depending upon your initial condition, depending upon how you set the flows and the latitude to begin with. It's not I don't think it's a unique answer that you get Joyce law. You get Joyce law if you begin with a 10 to the 5 Gauss field at the base of the convection zone. We're sensitive to the field strength. They're sensitive.
Come out. I mean, in terms of
Yeah. So
I go to the pole and all that.
But this depends upon how much interaction you have between the flux tube and the convection. And I don't understand convection. So I,
Yeah, if you believe ash convection, those
Yes.
dynamo convection, then it'll produce Joyce wall. It'll be tilted already.
yes. Yes. So I don't think we understand the large scale convection. And I'm not really in a position to speculate.
Actually,
Oh,
if
so-
toroidal field, if the strong toroidal field are generated based on the convection zone, and they have to traverse the convection zone,
Yes, I guess you're right. Yeah,
then
I guess you're
it
right.
got to do this.
I guess you're right. I guess it's not coming from the base of the convection
Well,
zone.
in your
But-
observation says that. I'm not saying that.
The observations are telling me what's producing dorsal. It's, yeah.
So it's like all the carbonate ones that start approaching surface, this enormous divergence flow creates this.
So Joyce, yeah, so Joyce law is basically telling you that the electric field in the, your feeder and your fire components of your electric field are related for each individual emergence. This is what, Joyce law is telling you. And the observations as to the different components is telling you that it's a surface, the north-south surface flows carrying the radial field, which is, producing the separation.
Yeah.
I agree with you. This implies constraints on the subsurface, on the dynamo, on what's happening beneath the solar surface. I would be much happier in discussing exactly what it was if I understood why we don't have giant cells, why the convective, the answer to the convective conundrum. Without that, I feel I'm missing a key part of the puzzle, and it limits what I can say with certainty. So this is observation, and I think this is the important part of this talk. And this observational analysis, by the way, was done by Hannah Shunker, his second author, because it's a super nice observation, and this is what it is. Any questions?
Other questions? And from online? Any question? Okay, if not, let's thank speaker again.